Right. Let's see. Couple of announcements. I posted the data set and the code that Dr. Gainanova mentioned and used in her guest lectures. So on eCampus under course content, there's a folder named Gainanova that her stuff is in. What I want to do this week is wrap up our coverage of the Introduction to Statistical Learning material. And there's 3 chapters that I want to touch on. The first is what the authors call moving beyond linearity. So I'll say something about that today. The idea is that in usual linear regression, the type of linear regression models that you see in a STAT 101 class, typical models are characterized by linearity. So you might have a linear regression model. If we have a numeric response y that is of this form. So maybe we have p predictor variables. That is a linear model in the sense that it's linear in the covariance. So it's constant times covariate plus constant times covariate. That often does very well. It's very simple, or relatively simple, compared to what we'll see in just a second. So in terms of having interpretability, which is one criterion that is useful for characterizing methods, a linear model is relatively easy to interpret. A beta coefficient is a mean difference in the response associated with a 1-unit increase in that predictor, holding all the other ones constant. Relatively straightforward. Often, simple models do pretty well compared to more complex ones, especially when you don't have an enormous amount of data. But remember, we've talked about trade-offs between model complexity and operating characteristics of a model. So we might, for example, consider accuracy. The more complex a model is, the more sophisticated, the more wiggly, nonlinear it is, the higher the accuracy on training data. But remember that there's the potential that beyond a certain point, more and more model complexity will result in less accuracy in the general population, what we call the test error. We also saw a picture kind of like this in the slides, where model complexity was on the horizontal axis, and then interpretability was on the vertical axis. So the more complex a model is, the less interpretable it is. A linear model, if the beta coefficients are relatively easy to understand and explain, something like a tree-based method, a random forest, or a support vector machine, one of these more black box type methods, they're harder to tell somebody what is actually happening. They may have accurate predictions, but it's harder to say what role the different variables are playing. So, for today's purposes, we're going to look at the chapter called Moving Beyond Linearity, and I'm motivating it with this regression model. So, simple linear regression model can be made more complex. by allowing for nonlinear relationships. One really simple way to allow for nonlinear relationships in a regression model is to include polynomial terms. So let's consider the case where there's just one numeric response and one numeric predictor. So our data can be represented as a scatter plot. Each observation, each individual has a response and a predictor variable that's measured. If that's our data set, we have a sample of size n, observations taken from an appropriate population. We want to model the relationship between y and x, either for prediction purposes or explanatory purposes. And maybe we see a scatter plot like the one that I drew. The scatter plot, I drew it in such a way that it looks reasonably linear, but you can see just with the naked eye some nonlinearity. So if I tried harder to follow the shape, it's more like the green shape. It's curvy. So if we have data like this, and I want to model y in terms of x, I could use a linear regression model. I could use the simple linear regression model that's written on the slide currently with just beta 0 plus beta 1 x. That model, though, assumes that it's a linear relationship. So it would be fitting a blue line. It'd be looking for the line that best accommodates all the points. In terms of what's the overall effect of x as you change x, what tends to happen to the response, you'd get a reasonable picture of it. You'd get a reasonable estimate, and your inference would probably not be too far off. But to the extent that there is a nonlinear relationship between x and y, we would be better off if we used a model that allowed for that. So what are our options if I want to consider models of the form of the green curve as opposed to just a linear one? I mentioned already one possibility would be to, instead of a linear model, use a polynomial model. So that would look like this in the case of a polynomial of order 2. That's still a linear model in the sense that it's constant times covariate plus constant times covariate, but it's not linear in x anymore because x is in a quadratic form. If I were to fit a model of that form, I could use the usual functions in R like Lm, and it would give me back beta coefficients. If I drew the fitted curve on the scatter plot, it would look a lot like the green curve. It's not restricted to be a straight line anymore. It can be curvy. It is restricted in terms of how curvy it can be. I'm only allowing, with this second model, for a quadratic curvature. So if the scatter plot suggested a change in the curvature, so maybe it curves concave, and then beyond a certain point of inflection it starts to curve convex, then a quadratic model would not be sufficient to capture that. But you could continue adding higher order polynomials to a regression model. So one really simple way to accommodate nonlinear patterns between response and a predictor is polynomial regression. One immediate challenge, though, of doing that is that interpretation becomes much harder. In the first model, this beta coefficient is the usual mean change in the response associated with a 1 unit increase in x. In the second model, though, you can't interpret that beta 1 in the same way. The way that we interpret beta 1 in the first model is we consider two individuals. So here's individual 1 with covariate x equal to, let's say, x star plus 1. And we're going to compare to individual 2 who has covariate just equal to x star. So I'm just dreaming up hypothetical individuals who differ by 1 unit on the predictor variable. Beta coefficients in a linear model, in a linear regression model, are mean changes in the response associated with a 1 unit increase in the predictor. So you can see that explicitly if you write out what the model is for each of these two individuals. Individual 1, we have our model saying that the mean response for this individual is equal to our line evaluated for this individual. The regression model is all about means. It says the mean response is a linear function of x. So individual 1, according to our model, has mean response beta 0 plus beta 1 times x star plus 1. Whereas individual 2 has mean response just equal to beta 0 plus beta 1 x star. And if you take the difference between those two, let's take the difference, we're left with just beta 1. The beta 0's cancel, the beta 1 x stars cancel. So in terms of saying what does beta 1 mean, how do you interpret it, you can see it explicitly by writing this type of expression. Beta 1 is the mean change in response associated with a 1 unit increase in x. Or in other words, it's the difference in the mean response that you would expect comparing two individuals who differ by 1 unit on x. If you have additional covariates, suppose we have x and z, yi, beta 0 plus beta 1, xi, and beta 2, zi. We can do the same exercise. What's the interpretation of beta 1? We can compare the mean response when x equals x star plus 1 and z equals some particular value z star. We could compare that to the mean response when x is 1 unit less and z is the same as the previous line. These two quantities, beta 0 plus beta 1, x star plus 1, plus beta 2, z star. And in the second case, we have beta 0 plus beta 1, x star, plus beta 2, z star. And if you take the difference now, you again have beta 1. Beta 1 is the mean change in the response associated with a 1 unit increase in x. And now that we have additional covariates in there, we have to specify while holding the other covariates constant. If Z is one thing for the first individual and it's a different thing for the second individual, I can't have this difference be just equal to beta 1. So in a multiple regression model, the beta coefficients are mean changes in response associated with a 1 unit increase in that covariate while holding everything else constant. So now let's go back to our quadratic model. Beta 0, beta 1, xi, beta 2, xi squared. And let's think about what's the interpretation of the beta coefficients now. Using the same approach that we used in the previous two examples here, suppose we tried to compare two individuals who differ by 1 unit in x and take a difference. It doesn't work out as cleanly as it did in the previous example, because if you increase x by 1 unit, then this is affected, but so is that. So you can't isolate beta 1 as a simple difference in expected values like you could with the other models. Once you allow for more nonlinear relationships in a model, the interpretation of the model coefficients becomes more complicated. So if you were to imagine beta 1 trying to interpret that as a mean change in response associated with a 1 unit increase in x, you'd have to say holding x squared constant. And you can't increase x while holding x squared constant. So my point with all of that is just we're going to talk now about moving beyond linear models. One big drawback is that the interpretability of a nonlinear model is more complicated. Remember what we've said about interpretability, by the way. Interpretation is not everything. Even if I can't tell you how my model is working specifically and what role X is playing in my predictions, even if that's the case, I may still be perfectly happy with my model. To the extent that all I really care about is prediction accuracy, who cares whether I can interpret what the different variables are doing? So whether or not you care about interpretability will depend on the setting. Sometimes people care about interpretation. Sometimes we don't. All we care about is accurate predictions. It's in the context where we're less concerned about interpretation and more just about accuracy that nonlinear and the really complex predictive models are most appropriate. So we'll talk today a little bit about nonlinear models. On Wednesday and Friday of this week, I'll talk about tree-based methods. Maybe you've heard of random forests, for example. This is a tree-based predictive model. And they're going to be hard to interpret. Not easy like a linear regression model for sure, but they often can be more accurate than simpler models. Can't interpret them very well, but they often bring higher accuracies. So, this is the context right now. We're considering going beyond just a linear regression model to something more sophisticated. Okay. So let's go to our notes. Their first slide says, the truth is never linear. What they mean by that is a linear model is almost certainly a simplified picture of reality. We don't expect that as you increase dosage of a drug by 1 unit, you necessarily change the response by some particular consistent number. But linear models are often close enough to give us insight. Our options, when linear is not sufficient, include these bullet points. Polynomial, that's what I was writing on the whiteboard. If beta 0 plus beta 1x is not sufficient, then why don't we add beta 2x squared? And we could keep going, make it a cubic, quartic, and so on. Another option would be step functions. A step function would look like, here's x, here's y. A step function would look like stair steps. What's nice about a step function representation is that it can be it's completely arbitrary what pattern is captured. In particular, it's not restricted to keep going up or keep going down. It's not restricted by any amount of curvature, so it doesn't have to have like a quadratic type curve or a cubic. It can be anything it wants to be. A drawback to a step function is that it's coarse. It is this discrete jumps from level to level, so it's not a smooth curve, which may or may not be an issue. But step functions are one way. Something called splines are another way. And a spline is basically a mathematically sophisticated way to do curves. Suppose that's the curve that I need in order to represent y related to x. That doesn't look like a quadratic. It doesn't look like a cubic. Maybe if we keep going up and up and up with the dimension of the polynomial, it'll get to where it can capture that well, but doesn't naturally look like a polynomial. It's just a smooth, wiggly curve. And it turns out that you can represent a smooth, wiggly curve of arbitrary wiggliness using a small number of parameters. If it was a quadratic, then I just need a beta 1 for x and a beta 2 for x squared. And I can represent a quadratic curve. If it's cubic, I just need one more beta coefficient. So suppose I wanted a wiggly curve that, in a similar way, has 5 degrees of freedom. It's not a polynomial, but I want an arbitrary curve, smooth, continuous function, that in some sense has a predefined budget of wiggliness that it can spend when fitting data. A spline is a way for doing that. So a spline is a way to say that y is a smooth function of x. And we have to specify some number of degrees of freedom. The math is going to be outside our depth pretty quickly here, but think of it as all we're doing with a spline is representing an arbitrary, smooth, curvy function, and we get to decide how wiggly it's allowed to be. This red curve, if I changed what I'm calling the degrees of freedom, if I were to lower the degrees of freedom, that would mean it can't curve quite as much. So it has to move more slowly. If I were to increase the degrees of freedom, then it gets to wiggle even more. So a spline is a way to mathematically represent a class of functions like that. And you can use exploratory techniques to decide just how many wiggly budget points are merited. So I'll show you a little bit about splines. A related model type is called local regression. And the idea there is a sensible idea for fitting a curve would be, let's draw a picture. I want to model the relationship between y and x, and I have a scatter plot that looks kind of like this. I could try fitting a linear model that would kind of go through the bulk of the points, but it wouldn't capture the curve. A local regression, essentially what it does is it breaks the x-axis into windows, little bins. And imagine within each bin, you fit a line. Suppose you were to go bin by bin and fit a separate little line segment within each. And then suppose that you can manipulate the mathematics behind doing this to enforce that this is continuous, that all the endpoints meet together, and it's has a smoothness to it, not a step function, but basically connected line segments that are restricted to move smoothly. In R, I'll show you a built-in function that's very helpful for guiding the eye in a scatter plot called low-s. So if you've ever heard of low-s curves, that's local regression. It's a smoother curve. Related to all of those is something called generalized additive models, which is a class of statistical models that these people, these authors, Tibshirani and Hastie in particular, developed. Again, as a general way of representing a smooth curve in a regression framework. So all that to say, there's lots of tools out there for working with models that aren't quite suitably modeled with a linear model. Keep in mind, interpretation becomes more complicated as you increase the complexity of the model. All right, polynomial regression is what we were talking about at the beginning. Here is a model where there's just one predictor variable, x. But we don't think a simple linear regression or linear model is sufficient. Down at the bottom, the scatter plot on the left is x versus y. Age, in this case, is x, and wage is y. You make a scatter plot of age versus wage, and you see the gray dots. Suppose you made that picture, and you just look at it without the blue curves on it. Suppose you just look at the gray scatter plot. Might not be easy to tell what is the nature of the relationship. Is that a linear relationship or not? With this particular picture, it might be hard to tell. For one reason, because the way the picture is made, there could be lots of gray dots on top of each other. You can't tell from the way this picture is made if some of these gray dots represent multiple dots sitting on top of each other. And if that's the case, then you're not really getting the full picture of the trend. So often, pretty much every time I make a scatter plot with real data, the next thing I do is add a smoother curve. A curve that the data uses, a data-dependent curve, to help guide my eye. Just looking at a scatter plot by itself can be hard to see. But if you add a smoother curve, like a low-s curve, like the blue curves, that can make it clearer. This does not look like a linear relationship. You see a U-shaped pattern, increasing trend for lower ages, which transitions to decreasing trend for higher ages. So just to reiterate, in the real world, you have a data set and you want to model a response in terms of a predictor. You need to think, before hauling off and fitting models, you need to think about what are appropriate models. With this data set, a linear regression model is arguably not appropriate because it misses some important structural features of the data. These data are not linear, they're curvy. So suppose that in this case, we make that scatter plot, we add the smooth curve, and we determine that I think a polynomial of degree 4 will be sufficient. That does not look quadratic. It's too flat. It's flat in the middle, more so than I would expect with quadratic. You could try a cubic, although a cubic is going to want to change curvature. If that didn't work, you might consider a degree 4 polynomial. So the authors suggest a degree 4 polynomial. You can easily do that by making it as though you have 4 predictor variables. So define your first predictor variable as x, and your second predictor variable is x squared, your third is x to the third, and then x to the fourth. Then fit this model. This is just a multiple regression model. And I can get beta estimates by treating it as though I have 4 predictor variables: x, x squared, x cubed, x4. If you've had a regression or a linear models class, you maybe are familiar with this type of model representation. Suppose we have this regression model. So just a numeric response, and let's say p numeric predictor variables. This is one way to represent the model, yi equals beta 0 and so on. An equivalent way is to say the vector of responses, n by 1, equals what's called a model or design matrix that's n by p times a p by 1 vector of beta coefficients, and then a vector of errors. This is equivalent to this model. In this case, capital X would be a column of n ones, and then a column containing x1. So here's the value of x1 for individual 1, then individual 2, individual n, ... The last column would be predictor variable p for individual 1, individual 2, and so on. Whenever you ask R to fit a linear regression model, behind the scenes, it represents things this way. Partly because once a regression model is written in this matrix form, it's straightforward to estimate it. There's a general result that says beta hat. The vector of coefficient estimates is x transpose x inverse x transpose y. And the variance covariance matrix of beta hat is equal to, under appropriate assumptions, something that's also easy to compute. So if we wanted to do a polynomial regression model, I'm treating it as though I have one predictor that's x, I have another predictor that's x squared, and so on. It just looks like usual regression. I would have x in one column, then I'd have x squared in the next column, and then x cubed, and so on. But in terms of fitting this model, it's not mysterious or complicated at all. It's very easy to fit a polynomial regression model. I will comment as a reminder, though, the interpretation of any one of those beta coefficients is now hard. What's the interpretation of beta 2, for example? If you try to go down the usual path, beta 2 is the mean change in the response associated with a 1-unit increase in x squared, holding everything else constant. That's hard to even get your head around. It's not very interpretable at all. Keep going. Here is an example of step functions. It's the same data set. So bottom left is the same scatter plot with the gray points. But instead of a polynomial of degree 4, we're using so-called step functions to represent the data. So you can see that the fitted, quote, curve takes a fixed constant value over one bin, then it jumps to another fixed constant value over this middle bin, and then jumps down to yet another value in the last bin. Step functions are the most flexible, the least restricted of all of these methods we're considering for nonlinearity. A linear function is restricted. Once you tell me one point, I know all the other points. Quadratic, similarly, it's restricted to be of a certain type of curvature. A step function can jump wherever it wants to. How would you fit a model with step functions? Let's come over here and think about it. Suppose we have data like is in the slide, age versus wage, and suppose we decide between here and here, we're going to have one step level. Between x1 and x2, we're going to allow for another one. And then between x2 and x3, we'll have yet one more. So I want to fit a regression model. I want something like beta 0 plus beta 1 x plus dot, 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 that represents a step function. The way that you do it is using what are called dummy variables. So if you're doing regression modeling and you hear the term dummy variable, what's being talked about are made up categorical variables that are specifically used just to enable a model that is desired, that's not smooth. So in this case, what we could do is create a dummy variable. Let's call my first, quote, dummy variable, let's call it U1. And this is 1 if x is in that first bin, x0 up to x1. So I'll make it closed on the left, open on the right. If x is in between x0 and x1, I'm defining this new, quote, dummy variable to be 1, and otherwise, it's equal to 0. Similarly, let's make u2 be a dummy variable, 1 if x is in the second bin, x1 up to x2, 0 otherwise. And finally, u3 So instead of using just x as my predictor variable, I translate my model to be in terms of these dummy variables that are indicators that turn on or turn off. Then we can write a regression model using those dummy variables. So suppose we say beta 0 plus beta 1 u2 plus beta 2 u3. Suppose we say that. Then remember u2 and u3, both of them are either 0 or 1. If u2 and u3 are both equal to 0, that means that the corresponding x is in that first bin. So we have an interpretation like this. Beta 0 is the expected value of y when x is in bin 1. If u2 is equal to 1, then necessarily u3 is equal to 0, because you can only be in one of the bins at a time. So I can say beta 0 plus beta 1 is the mean in bin 2. And then finally, beta 0 plus beta 2, if u3 is equal to 1, that means u2 is equal to 0. That uniquely places us in bin 3. Big picture, what I want you to kind of get from this is you can fit arbitrary regression type of functions. Okay? Certainly you can fit a line. That's basic linear regression. You can fit quadratics and other polynomials by just replacing x with x and x squared and x cubed and so on. You can fit step functions by using dummy variables. And we can keep going. There's additional ways, like splines. We don't have time to go through splines in great detail, but I will review it a little bit on Wednesday. Splines and generalized additive models. So think of the splines and generalized additive models that are coming as more sophisticated versions of step functions. Hopefully it's kind of intuitive that you can see how to do the step function thing. So imagine allowing for more and more steps while requiring that the resulting curve be smooth. One thing that step functions are not ideal with respect to is that they are so rough. They're these step functions. And in many cases, we would prefer to have a smooth curve. Splines and generalized additive models are ways of accommodating that. So the math is a little bit sophisticated, But conceptually, it's like allowing steps and restricting some smoothness. Let me see what I want to finish with. Let me just comment on splines. I want you to have at least heard of a cubic spline. This is a type of spline. Let me back up. A spline is kind of like the step function idea, where we bend the horizontal axis into mutually exclusive bends. Whereas with the step function approach, we restrict the mean to be a constant in each bend. We could get more flexible and allow for, say, a linear function in each bend. That'd be a piecewise linear, or a quadratic, or a cubic. We can generalize that way. And the higher the order of the polynomial within each bend, the curvier the function is allowed to be. There's some math that suggests if you want to estimate an arbitrary function, you draw a scatter plot x versus y, and there's some curve underlying it, and you want to estimate it with data. There's some theory to say the best way to do it is with what's called a cubic spline. What a cubic spline is like a step function where you bend the x-axis into mutually exclusive intervals, and then within each one of those, you fit a cubic polynomial. So a cubic spline, you pick what in the language of splines is called a knot, or places where there are, quote, knots. Those are like the boundaries between the bends. You pick the knots, and then the math will fit a piecewise cubic polynomial that's restricted to be smooth. What we mean by smooth is not like that, but like that. So differentiable. You can't take a derivative at this point because it's pointy. So a spline requires polynomials within bends subject to a restriction that they're differentiable. And specifically, we need second differential, or differentiable twice for cubic splines. Again, the math behind cubic splines and splines and spline bases and stuff like that is beyond the scope of our class. But you don't have to know the math to be able to use it in practice. So it's relatively straightforward in R to say I have a response and I have a predictor. I think there's a nonlinear relationship between the two. I don't want to say it's quadratic or cubic. I don't know what it is. I think it's curvy. I want to use a flexible technique to do a regression model with a curviness. Splines are a good choice. Out of time, but I will show you before we're done with this coverage how to use at least the BS function. Because if you want a regression model that's based on a spline, it is as simple as using LM, where you say response tilde, and typically, if you wanted to do just a linear regression model, you would say y tilde x. If x was a single predictor variable, that'd be a simple linear regression model. In order to allow for a curvy relationship, you just need to insert the BS function. BS stands for B splines. So it's just splines. And there is an argument to the function that allows you to say how wiggly does this spline get to be. By default, the degrees of freedom is 3, and that corresponds to a cubic spline. All right, we are out of time. I'll show you what this looks like in practice, but like this red curve right here, we can have that red curve, nonlinear model, using LM if we replace X with a spline wrapper like BS. Okay. Yeah, I'll let you go. One thing that we'll have to think about, though, is where do these knots go? The knots are locations that separate the bins. We're going to fit little cubic polynomials within bins. How many bins do we need, and where should we put the knots is an open question. What general technique do you think we could use? Suppose we have training data, and I want to fit y as a curvy function of x for prediction purposes. I'm going to use a natural cubic spline, but I don't know how many knots to use or where to put them. What technique do you know that we could use to ask the data? Where should I put the knots and how many of them? Bootstrap could be used, and so could cross-validation. Choosing how many knots and where to put them is kind of a tuning problem. So all this supervised learning stuff, you choose a class of models and then you tune it using either a train test split or cross-validation. Okay, I will let you go. I will have a Q&A tonight, and I'll do some coverage of your practice homework assignment.